Great. Hello, everyone. I'm Andrew Poelstra. I'm here to talk about a fairly specific application of zero-knowledge proof set. I think, well, it's a specific application, but I think it generalizes a lot. The last few talks have been kind of taunting me in that they all are very close to solving the problems that I want solved, that I'm going to talk about here, but none of them are quite there. I had that with Nick's talk about VRFs, about PORFs. I'm missing a letter there. And then with Merlin, everything was so wonderful about Merlin, and then it's going to be completely inapplicable to everything that I'm doing here. So let's get started. So here we have, oh, my battery is dead here. Oh, there we go. Oh, it's just slow? I have to point it at the computer. I've got it. OK. This is a Schnorr signature. This is the simplest possible Fiat-Shamir transform. It's like the standard example of a Fiat-Shamir transform. It was patented by Schnorr, not by Fiat or Shamir. But I mean, that's how these things go. So the way this works is pretty straightforward. You have some sort of key pair. You want to produce a digital signature of some sort. So you think up this uniformly random thing K. It's basically this ephemeral key pair. And you convert that into an elliptic curve point, or whatever discrete log hard group you might have. You convert that into a public point. You hash everything. You get your challenge here. And then you compute this linear equation on these two random secret values. One is this ephemeral key that you're using for the signature. The other is your actual secret key. OK. And as Henry mentioned, the way this is written in papers, of course, is basically like this. You have this K gets $sign here. It's uniformly random. What could be harder than that, right? And then similarly, E here is your challenge. It's just a hash of a bunch of data. Again, what could be harder than hashing a bunch of data? There's not even, E is just a reply from your counterparty. The hash there is a Fiat-Shamir transform. OK? This is great, except that it's not, of course. This is very difficult to do in practice. And there have been many examples of people generating their randomness in defective ways, either by outright reusing nonces or just by leaking a couple of bits. And there was a paper this year that I think was presented at RWC down the road a couple months ago by Joachim Breitner and Nadia Henninger, analyzing the Bitcoin blockchain and finding a whole bunch of signatures that had been generated, not Schnorr signatures, but ECDSA, which is basically the same but not patented, in ways that were biased in a way, and biased dramatically enough, but not like reusing Nonce kind of biased, just like biased subtly in a way that would apparently be invisible, but using lattice techniques, you're able to amplify that bias. OK, so this $sign is hard. As Henry mentioned, even this hash is kind of hard. And the thing is that Merlin will solve all of this, and you will have no more problems if you're generating signatures using Merlin at both of these stages. OK, and I mention this in my next slide. I say RFC 6979, which is a standard version of Merlin, which solves none of the problems Merlin does, other than being deterministic. This has a couple limitations that are not so important for single signers, but I'm going to go into the multi-signature setting in a sec, and then they're going to become important. A big one, well, actually, an important one, even for single signers, is that there's no way that you can prove as a signing producing device, or some sort of hardware token or something, that you used RFC 6979, or that you used Merlin, for that matter. If you have some sort of hardware token that's supposedly signing cryptocurrency transactions or something like that, it should really be generating its nonces uniformly randomly. And you, as a user of this token, would ideally like to be able to verify that it's generating these uniformly randomly. So it's not just mistakes that might cause these nonces to be biased and leaking secret key material. It could be a malicious hardware manufacturer, or somebody who intercepted the hardware along the way, or some software guy, or who knows, like anywhere along the line. And what you as a user get is just a signature. OK, and from the signature, you can't tell how the nonce was generated. There's no hint of anything. So we're at the ZKP workshop. We all love zero-knowledge proof. So why don't we say, let's just throw a ZKP on here. OK, the hardware wallet's generating this randomness supposedly in a safe way. Supposedly it's using Merlin. How about we just make a ZKP that it ran the Merlin code? OK, wouldn't that be great? Well, I mean, zero-knowledge proofs are randomized as well, right? So if your hardware device is outputting a zero knowledge proof, then it can just leak randomness in the zero knowledge proof by tweaking the random nonces that are used in the ZKP. Okay, so you need to trust your host, right? You're not going to publish these zero knowledge proofs, of course, but if your host is compromised, then who knows where those proofs are winding up, right? And if you can trust your host, there's a much simpler thing. This is not so relevant to the rest of my talk, but I'm just going to keep shilling this in front of everybody who I think might be implementing hardware devices to say, like, please do this. What you can do in the specific case of producing single signatures is you can have your hardware device basically propose a nonce, let's call this R0 here, and then your host, if we're going to assume that the hardware device or the host, but not both, are going to assume that at least one of them is uncompromised, okay? The host provides its own randomness that I'm going to call C here, and the hardware device just kind of mixes it in. And so you do this signature protocol where your public nonce has randomness contributed from both parties, both the hardware device, which is maybe compromised, and your host, which hopefully is not. Or alternately, maybe the hardware device is honest and the host is compromised, whatever. But you can kind of double up the security in a much simpler way than throwing general ZKPs on here, or than doing like a multi-signature between the host and the hardware wallet, or some sort of MPC or whatever other scheme you might think of. Okay, that's single signatures. Okay, Henry pretty much covered all of this. We solved everything with Merlin. But now, let's move on to the multi-signature setting. So Schnorr signatures admit a very nice form of multi-signature where you can kind of compress all of the participants' public keys into one. You can do this basically by just summing them up. I have these little randomizers, mu I, in here. That's part of a scheme called musig that I developed with a few of my colleagues to prevent keys that are adversarially selected. This is important for getting multi-signatures that are secure in the plain public key model, where you don't have any authorities or attestation or anything like this. It's very straightforward. We saw from the equation a couple slides ago, we just do this linear equation and all the secrets. So basically, everybody does this linear equation in their respective secrets. You sum up the results, and you wind up with this cool signature, which has just a single public key, which is a sort of randomized sum of the participant's public key. The single nonce, which is a sum, it doesn't have to be randomized, it's the sum of all the participants' nonces. This message M, I guess, that they all agree on. And they all wind up with a single signature, which is just the sum of all of their individual contributions. And the issue here is that when these parties are generating their individual contributions to the nonce, they again have this problem where they need to produce uniform randomness. And the partial signatures that they produce that wind up being summed to the full signatures need to have this uniform randomness in them. But what the partial signatures are signing is no longer this challenge E, which is a hash of the individual participants' stuff. It's now this challenge E that can include input from everybody participating in the protocol. Which means that if you were trying to deterministically generate your nonces by hashing all of your own inputs, by hashing the message, by hashing your labels, whatever good best practice protection you want to use, if you're using Merlin, that's not going to help you. The reason being that at the end of the protocol, you are going to have to produce a linear equation of your secret data involving this challenge E that has contributions from everybody. So if you generate your stuff deterministically, and you get halfway through the protocol, you produce a partial signature, and then you're reset, or you're asked to sign the same message twice. You don't even have to be reset here. You can just complete the protocol twice. And another participant provides a different contribution to the nonce. The result is you will create two partial signatures on the same hash, or sorry, using the same nonces, but different challenges, and you will leak your secret key, okay? And there's not really anything you can do about this. It's kind of inherent to these multi-party unordered protocols that there's nobody who really goes first. Like always, the person who chooses, well, everybody except the person who chooses their nonce last has to accept that their challenge is in some way being controlled by other people. So we can't use deterministic nonce randomness. Or if we can, we still need some sort of entropy seed from somewhere. So like, are we back to physical randomness? Do we lose all these benefits of Merlin that we just talked up for the last half hour? Well, it would seem so, wouldn't it? But this time we can use zero-knowledge proofs to save the day. And that's what I want to talk about. So suppose instead, so each party, and everywhere you see 6979, just replace it with Merlin. I had to submit my slides to the computer before 30 seconds before my talk, so I didn't get to change it in light of everyone else's talks. So everybody is going to generate their randomness deterministically, but this time they are going to provide a zero-knowledge proof that they did so. And so the cool thing here is that now, rather than worrying, like, oh, if I use deterministic randomness, then if I get reset, or if other parties change their stuff, then I get screwed. We're now saying everybody has to use deterministic randomness. So as soon as the parties agree on whatever public data there is, the set of public keys, the message to be signed, the signature scheme, the label, all your good best practice stuff for domain separation, then at that point, the idea is that basically everybody's transcript is going to be unique. Okay, there's only one thing that they can produce if they're doing a multi-signature, assuming that everybody is actually submits all their data. And if people just don't participate, if they back out, it doesn't matter. The multi-signature fails. That's the nature of a multi-signature. Okay, so what would be nice if we could just take Merlin and throw it inside, turn it into an arithmetic circuit, and then produce a zero-knowledge proof using one of the many general zero-knowledge proof schemes that people in this room have invented. Well, when you try to prove that secure, suddenly you immediately start getting nervous, okay? Because you've got this non-interactive zero-knowledge proof whose security is defined by this weird simulation argument, and you're going to try to do this argument that you're still producing secure signatures where the Fiat-Shamir transform that you did on the signature now also has this ideal in a real world shift. You start becoming very nervous trying to prove this. In fact, you run into some difficulty trying to prove this. So what we need is actually not just throw a hash function in a ZKP. I mean, that would be sufficient, but if you're trying to prove security, what you want basically is to take a PRF and put that into a ZKP. And the result, there are two ways to think about the result. One is you take a PRF inside a ZKP, where the PRF input is going to provably be your secret data, I guess your secret key, and then all the public stuff. Another way to think about it is a weird kind of VRF. A VRF, we remember from Nick's talk, is a verifiable random function, where you output this public nonce, and everybody can verify that you generated it deterministically from the data that you were supposed to generate it from. It's not quite a VRF. And the reason, and this just really taunts me, is that with a VRF, the output is kind of the public data. And what we need here is that the output is not just a public nonce. You also need to have a secret nonce corresponding to that. You need to output this uniformly random looking curve point, but you need to know the discrete logarithm. And every VRF that I've seen out there generates these points, generates their output through some sort of hash to point scheme where you lose the discrete logarithm. And this is really inherent to how you can argue that these things are even secure. So every time I see a new VRF paper, I read it, I pour through all the equations saying can I get a discrete log out of here? And you can't. You just never can. And it's never written in the abstract that you can't do that, because why would you ever do that? So we have a solution to this thing that I'm actually not going to talk about today, because I mostly want to talk about problems. Solutions are for customers, but problems are for cryptographers, and that's who's here right now. So Peter and Yannick Sarin and Tim Ruffing and I, well, not really me, not me. These guys are on an email thread that I'm CC'd on. So that's my contribution. Have developed a solution to this where they have a PRF which is heavily optimized for use in arithmetic circuits. It's less than 2048 multiplication gates, and it has provable security. We believe, we aren't done the paper yet, but we have good reasons to believe this is secure, based on the decisional Diffie-Hellman problem for a couple of elliptic curves that we've generated that are defined in relation to the specific ZKP scheme that we're using. But you can generalize that. You have to generate new parameters. But we have a scheme. Basically, it's based on a paper that argues that if you take a 512-bit curve and you generate some sort of random curve point using some secret data, and then you take the first half, the first 256 bits of the x-coordinate, of the 512-bit x-coordinate, then you can get something that is provably appears uniformly random, assuming DDH. There's a paper about that, and we plug in a few things there, and we've developed what we believe is a solution that we hope to present next year or before the end of the year. But that's ongoing research. But I'm going to talk about more problems. Instead of dwelling on this solution to the multi-signature thing that we've developed using ZKPs and spent a lot of time optimizing, I'm then going to make the problem even harder here and start talking. But rather than okay, so let me quickly summarize what I just said. So we use a ZKP, we turn our randomized signatures into these sort of unique ones, by which I mean signatures with unique transcripts. If you ignore all these zero-knowledge proofs that themselves are not unique, that's sometimes useful. We eliminate a bunch of replay attacks, and now what I'm going to go into is threshold signatures, and I'm going to talk about the need for broadcast channels in certain cryptographic protocols. So Henry mentioned a few things about the way that academic papers are written, where you sort of take the Fiat-Shamir transform as something that's up to the implementer. You take your random number generation as something that's up to the implementer. There's another thing that's often not thought about, and actually Henry briefly mentioned it with his like ideal people somehow doing math, is what do your communication channels look like? What happens if you have a multi-party protocol and some parties are sending inconsistent data to different parties? What happens if somebody's just not sending data that they need to send, that kind of stuff? And usually when you think about this, you get into the domain of things like Byzantine fault-tolerant consensus and stuff that's cryptography adjacent, but never really touched on in crypto papers. And one major class of cryptographic schemes that are guilty of this are threshold signatures. So let's talk about threshold signatures real quick. So threshold signatures are like Schnorr multi-signatures, where you add up everybody's contribution. Everybody sort of generates some contribution. They add up each other's contribution. They hash that. They generate a partial signature, add that. Everything's great. We're going to do exactly the same thing, except now we're going to say, well, we don't need all the participants. And the way we're going to avoid using all the participants is that everybody is going to shard their contributions to the protocol. And they're just going to send shards of their contribution to everybody else. And the idea here is that if some party is not present for the actual signing, so during key setup, everybody shards their key and spreads that, and everyone needs to be there for that. But during signing, if people are missing, the other parties can use their key shards. They can Lagrange interpolate this. What they actually do is they just use the shards and produce partial signatures of the shards, and then Lagrange interpolate the partial signatures themselves. So no secret data is ever interpolated, just the public signatures. And then you can produce a threshold signature. Okay, you can do like a 2 out of 3 signature or something like this. Okay, and there's a standard paper about this by Stinson and Strobel in 2001. It basically does exactly what I just said. There are a few new things to think about here. One is, how do you do the sharding? There's kind of a standard way to do this, standard-ish, or like a realization of a folklore way of doing this from Pedersen in 1991, where you just send out shares to everybody, everyone can Lagrange interpolate it. And the way that you deal with some party sending bad shares to certain other people is that you have this kind of challenge scheme where somebody can say, hey, my shares don't match up with the polynomial they're supposed to be generated from. The way this is done is that during the sharding process, each participant generates a random polynomial, and they send like a public witness to this. They convert all their coefficients into elliptic curve points and publish those. There's a problem with this that I'm not convinced is a real problem, but it's nonetheless a problem, where one party can kind of abuse this challenge thing. They can become like the balance of whether or not the protocol succeeds or not, and bias the resulting public key or public nonce. If they say, like, I want the 0th bit of this public key to be 1, they can like always abort when that's not going to be the case and somehow bias this. Does it matter if you're biasing public data? I don't know. I don't believe it does. But I mean, it certainly means that your key is no longer coming from a uniform distribution. So your security proofs don't go through. And it's very dangerous to like throw away all your security proofs for something that doesn't matter in general. It just always is. So there's a Gennaro, Jarecki, Krauswitz, and Rabin came up with an extension to this where you have these challenges and then like a way to defend against the challenges, and this prevents this certain forking attack, and everything's okay. Okay, so that's nice. But there's another thing. So there are a few different schemes. There are a few different ways that we can simplify this protocol, or that I think we can simplify this protocol. But no matter what, we're going to need a broadcast channel. Okay? So we have the problem with this secret sharing is that we have a much more complex multi-party protocol. And again, because it's a multi-party protocol where everybody's throwing contributions in at the same time, it's difficult to use general techniques like Merlin to try to do best practice defense against these things. So we went back and forth. We've been trying to design kind of a fail-safe API for this. And we've gone back and forth. We have a few different ideas for how to prevent this, or for how to simplify things. One is that we could use publicly verifiable secret sharing rather than the just regular verifiable secret sharing. Then suddenly this challenge and defense thing kind of goes away because you have cryptographic proof that somebody's misbehaving. Except not really, because if somebody just doesn't send any data, you can't cryptographically prove they didn't send you the data they were supposed to. So there are other schemes where you like publicly encrypt secret data to everyone instead of sending it to them privately. And you need a broadcast channel for all of these. Well, there's another way where you just don't secret share, where you secret share the key, and then at signing time, everybody says, hey, like everyone who's here, raise your hand, and we're just going to add up our nonces. We'll do the Lagrange interpolation on the keys, but not the nonces. And it's possible to do that actually without revealing secret data. But you always need a broadcast channel. The reason being that you need to worry about what people sending inconsistent data to each other or just not sending data to certain participants. And actually, I would love to be told that I'm wrong about this. A few of the authors of these papers are here. This is not explicitly mentioned in these papers. It's sort of assumed, and you can infer by the lack of subscripts that everybody needs to be seeing the same data at each stage of this. But it's actually not explicitly mentioned that you need a broadcast channel. So my last slide, yeah. No, that's not it. There we go. This is the last slide. So let's bring ZKPs in. And I had yesterday morning, I was really excited about this slide. This last line was not here. I was like, hey, we can get rid of the broadcast channel, okay? Because we can just throw ZKPs on here. We do this publicly verifiable secret sharing. Now, when people are sharding, not only do they generate their nonce deterministically, but they generate this whole polynomial that they're evaluating to get shards. They do that whole thing deterministically, and they publish that to the world, although they still have these secret shares that they need to communicate to people privately. And the trick is that as long as we prove that they did this deterministically, then everybody's transcript is unique, right? And so now it seems like we're back in the realm where if anybody is misbehaving, this can be immediately detected, or detected before the last step when people are producing partial signatures and leaking stuff. And we don't need to worry about like these forking issues. We can also reduce the number of rounds because we no longer have these challenges, we don't have defenses, all this good stuff. But there's something hiding in this entire transcript must be unique thing. It is, the entire transcript must be unique, but they cannot generate the transcript by themselves. Okay, and that was a part that I missed until yesterday morning, and I had to add this sad point that says that maybe we really do need a broadcast channel after all. The transcript can't be generated by themselves. So everybody still has to shard their things. They have to generate a uniformly random nonce. They have to shard this. They have to send this to everybody and publish their public coefficients. And only at that point can everybody compute the challenge, which is like the hash of the sum of all these nonces and stuff. And then everybody can produce their signatures. And so even though the result is completely deterministic, it's possible for somebody to like disappear partway through the protocol. And this is preventing this or recovering from this in a reasonable anti-fragile way. Yeah, I see I have 1 minute. It seems to be a hard problem. So the difference between multi-signatures and threshold signatures is that with threshold signatures, if somebody's screwing around and dropped out, if you have sufficiently many other honest parties, ideally they would be able to recover and actually complete the signature. Because that's kind of the goal of a threshold signature, is that you don't need everybody. So it would be nice if like these unnecessary people weren't able to grief the protocol. And so when we get this determinism, now the only room for griefing is that some party can maybe send some data to some participants and not send data to the others. And what this means is that this need for a broadcast channel, ensuring that everybody gets the same data, can now be weakened, possibly, weakened in principle, but maybe not in practice, to saying maybe we can just do set reconciliation. If somebody sends data to only one participant, or to half the participants, but not the other half, maybe that half can reveal what they learned. That's all going to be public data, the public points and the zero knowledge proofs. And maybe just everybody needs to get together and say, hey, here's all the data that I heard from anybody. And then they take the union of everything that everybody heard, and then you can do the protocol using that. Maybe that would be sufficient. I don't know. Unfortunately, I'm out of time. And I hope that made sense without any equations. I had to delete all the equations to save time, and then I don't know if that helped. But there we go. That is my talk. Thank you.
Okay, thanks.